Hi, my name is Jawad Gul and I'm bridge engineer in Lincoln, Nebraska. In this video, I'll explain the calculation of approximate section properties of complicated sections using numerical integration. An example spreadsheet can be found in the description link below. Here is a typical concrete segmental bridge section that I'll be using in this example. And the first step is to simplify the section. You can get rid of the cross slope at the top and the curves connecting the web to the top slab. These simplifications will slightly underestimate the section properties. Here is that simplified sections with dimensions on it. The top width of the section is 31.5 feet. The depth of the section is 8 foot. The bottom width of the section is 13.33 feet. And the webs are 1 foot wide. Once you have dimensions on your section, the next thing you need to do is to establish the relationship between the depth and the total width of the section. So at depth of 0 inch at the top over here, the width of the section is 378 inch. So we have 378 inch against 0 inch depth. At depth of 9 inch, the width of the section is again 378 inch. And just below 9 inches, let's say 9.001 inch, the width of the section is 120 plus 120, 240 inches. And that width gradually reduces and becomes 12 plus 12, 24 inch at a depth of 9 plus 9, 18 inches. And that stays pretty much constant to a depth of 9 plus 9, 18 plus 70, 88 inches. Just below the 88 inch, the width becomes 160 inches. It's a little bit more at this depth, but I'm assuming at 160 inches just to keep the things simple. If we plot this table, this is how it would look like. Notice how this complicated section has been reduced to this simple curve. I'll be using this curve to explain the numerical integration process, but it is not required for the numerical integration. Here is that curve that I'll be using to explain the numerical integration process, and the first step is to divide this curve into small strips. In the Excel spreadsheet posted in the description link below, I'm using 1 inch deep strip. The strips shown over here are not 1 inch deep and are for demonstration purpose only. So once you have divided your curve into small strips, next, you need to find out the area and moment of area of each strip. Let's say you have a strip at a d distance from the top. The area of the strip is simply the height of the strip multiplied by the width of the strip. The height of the strip is constant, 1 inch, and the width of the strip can be found by interpolating between these two data points. In the Excel spreadsheet posted in the description link below, I'm using a custom-made interpolation vlookup function that looks up the data table and interpolate between appropriate points to give you the width at any particular depth. So once you know the area of the strip, the moment of area of the strip is simply the area of the strip multiplied by its distance from the top, and that will give you the moment of area of the strip with respect to top. In this way, you can find out the area and moment of area of all the strips, and that can be done in a tabular form. Adding the areas of all the strips will give you the total area of the section, and adding the moment of areas of all the strips will give you the total moment of area of the section. And then dividing the moment of area with the area of the section will give you the distance of neutral axis from the top, because we computed the moment of area with respect to top. Now that we know the location of neutral axis from the top, we need to figure out the moment of inertia of each strip with respect to neutral axis. And we can use parallel axis theorem to do that. So the moment of inertia of each strip about the neutral axis will be the moment of inertia of each strip about its own centroidal axis plus the area of the strip multiplied by square of the distance of the strip to the neutral axis. The moment of inertia of the strip about its own neutral axis is very small and can be ignored. So the moment of inertia of each strip about the neutral axis would be simply the area of the strip multiplied by the square of its distance from the neutral axis, or y bar square. This y bar is easy to compute and will be simply the distance of neutral axis from the top minus the depth of the strip. Again, we can do this in a tabular form, and we can compute the moment of inertia of each strip. Adding the moment of inertia of all the strips together will give us the total moment of inertia of the section. Thank you for watching the video. The Excel spreadsheet tool is posted in the description link below. Please post your questions and comments in the comment section. Please like and subscribe to get updates on newly posted videos.